pleasure to welcome Dr. Dimitris Giannakis from the Quran Institute for Mathematical Sciences. So Dimitris did his undergraduate work in physics at the University of Cambridge in England. And then he did his master's there also at Cambridge. And for his PhD, he came to the University of Chicago, again in the physics department. And his PhD thesis was on a problem related to magnetohydrodynamics. But doing this work, he became interested in innovative methods of data analysis. And for the past several years, past 3 years, since 2009, he has been at the Quran Institute for Mathematical Sciences at NYU. So you may like to know, if you already don't know, that the Quran Institute is a very prestigious place for mathematical studies for a long time, known worldwide, but for the last, I guess, 10 or 15 years, they have developed a program in atmospheric and ocean sciences. And Dimitris is in that program, and he came there as a postdoctoral research associate, but now he's an assistant professor. And as you will see from his talk, his major focus is he's working on climate models analysis. Many people here analyze climate models, but his focus is in developing more insightful methods, which bring out more information on climate model outputs or climate data sets. So let us welcome Dimitris Giannakis.
Thank you very much for the invitation. So today I will talk about joint work with Andy Maida from Quran, who was my postdoc mentor, which was done over the last 2 years or so on analysis of spatiotemporal data from climate models or observations, and in particular a method that we call nonlinear Laplacian spectral analysis. So to start with the motivation, the goal here is basically that we assume that we have a high-dimensional time series that we observe that can be coming either from a climate model or from observations. And we want to break it up into a set of patterns. So here, schematically, we have some signal xt. We want to break it into a set of these patterns indexed by k. And we want to do this in a way that each of these patterns has some meaningful information about the system. And what I mean by meaningful is that it has some relevance for dynamics. So in this example here, this is just a toy example of a low-order, chaotic, deterministic system that is supposed to mimic zonal and blocking transitions in the atmosphere. You see a time series. This is the output of the model that has this chaotic transition, and you can imagine that you want to take this set of ODEs that is giving this time series, and you want to do dimensional reduction. So what that would involve is to find a set of modes that you project your original full equations, and you only retain a subset of those equations to arrive at a more simplified model. And so a standard way of doing that is through empirical orthogonal functions or principal components analysis, which basically projects the system into the modes that capture most of the variance. So in this particular case, one could imagine projecting a set of differential equations onto the empirical orthogonal functions, and then examining the skill of the resulting model by running it forward. And what happens here is this is a 6-dimensional model. Even if you use 5, so you leave out only one of these 6 modes, typically you'll do a very bad job in representing the dynamics. So this is an example of integrating a reduced model that was projected onto the leading EOFs, and you can see that basically it doesn't have any relevant to the original dynamic, it just decays to a fixed point. So in other words, what this is saying is that the states of the system which are those that have the most variance or the highest energy, which is basically the states that principal orthogonal decomposition or principal components analysis finds, are not necessarily the states that are important from the point of view of the dynamics. So, so the method that I will talk about today basically tries to find states which are more important to capture the right dynamical features, even though those states may not be the optimal from the point of view of capturing high variance. And so in this panel here, this is an example of a 4-dimensional model. So basically here we take the original 6-dimensional model and throw away 2 dimensions. But we do the projection onto the modes recovered by the method I will be talking about today. And you can see that qualitatively, the reduced system follows has some of the features of the original full model. Of course, it doesn't do it in a kind of like a point-wise trajectory sense, because this is a chaotic system. But qualitatively, you can see that it has this irregular transition. So it's doing a significantly better job than this case, for example. So, so the underlying motivation of this work is to basically, given a set of observations, how to break them up into several patterns, such that those patterns tell us something meaningful about the dynamics of the problem. So this is the outline of the talk. The first part I will describe how this method that we call nonlinear Laplacian spectral analysis, or NLSA in short, I will say the basic ingredients of this work, of this method. And in the next part, I will talk about applications in North Pacific SST variability from climate model output, and also in using the modes that we recovered to actually do predictions, so in regression type modeling. So I might deviate slightly from the outline, because I realize that there might be more interest here in an application that is related to the atmosphere and not as opposed to the ocean. So I will show some of slides from some other talk on some work that we have done on the MJO from satellite observation. So probably I won't have time to go through all of this, maybe not the third part, but there will be some other material relevant to atmosphere. So, okay, so this to begin with a description of the method. So the method NLSA combines ingredients from basically three distinct disciplines, namely the qualitative analysis of dynamical systems. So I will say what this means, but to those familiar, it involves doing things like time-lagged embedding of data to basically retain, to capture some of the lost dynamical information. And also singular spectrum analysis. This is the generalization of empirical orthogonal functions in lagged embedded data, and it combines those two tools with spectral graph theory and ideas from differential geometry. So basically, in a nutshell, what we want to do is to generalize the notion of principal components analysis to take into account the fact that the data sets that we deal with can be thought of abstractly as some sort of nonlinear manifolds embedded in the space of where the data is observed. So to give an example, if if we had our data set consisted of output of a simulation, let's say in the North Pacific, as will be the case later, we can envision this abstract space of all possible configurations of the model. This is Rn, where n is the number of grid points that we observe. But typically, the dataset that we will have will lie in a much lower dimensional subset of Rn. We will not observe any possible n grid point snapshot, of course. So, but the way this lower order, this low dimensional subset of Rn is produced is not accessible to us. We know that we postulate that it exists, but we don't have direct access to it. And what these tools allows us to do is to basically build a set of a dictionary, if you wish, of basis functions through which we can describe our data in a manner that is compatible with the fact that it forms some nonlinear lower dimensional manifold embedded in space. So, I will give now an overview of the basic steps of the method. I will be happy to discuss in more detail later if necessary. So the first step comes from the qualitative analysis of dynamical systems, is basically to consider, instead of single snapshots of, let's say, our model output as our individual data points, to consider histories or small chunks of dynamical evolution over a given time window, which we'll call lag window, this delta t here. So so in other words, what we want to do is we want to build in some of the dynamics in the vectors that we use to do data analysis themselves. If we were doing an analysis by any geometrical algorithm, be it empirical orthogonal functions or NLSA or what have you, on just a set of snapshots that we observe, the results of the analysis would basically not depend on, if we say did a random reshuffling of the snapshot, we would get exactly the same results. In other words, the algorithms don't know something about the underlying dynamics. But if instead of looking at individual states of the system, we consider a stack or a small portions of the trajectory over time, then within each of these collections of trajectories, we have embedded some information about the dynamics. So operationally, the way this is done is that we take our data set and we produce a bigger, let's say we had a matrix whose each column of the matrix was represented a snapshot from the GCM. We produce an even bigger matrix where each column now represents a history of length delta t of evolution from the GCM.
Just a question. So in your first slide, you sort of compare this method to just standard UF.
Mm-hmm.
Have you compared it to a standard UF in which you also do the time?
Yes. So this is basically common to, you can do, in extended UFs, you basically do, this is a step that is done also there. So this step can be done in many different approaches. So it is important because basically it puts some information from the dynamics in the geometry of the data. So each element in this lagged embedding space contains some information about the history. It's not just a stack of cards that is.
My question was that, do you try to see whether the extended UF does better than?
Yes. I will show. I will show this later. Okay. So this is kind of like the first step, and it's common to both EOF, extended EOFs, or the analysis that the method, this NLSA method that I talk about here. Now, just to make sure that everyone, to set the background, the standard way of basically processing the data once it has been whether it has been lagged embedded or not, is to take this big matrix where each column corresponds to an observation and do its singular value decomposition. So this type of method has many names. It's called singular spectrum analysis, principal components analysis, principal orthogonal decomposition, many flavors of essentially very, very similar things. But in a nutshell, what this singular value decomposition means is that you take your data set and you find the axis in the space of data that capture the principal axis that capture most of the variance. And so you have a covariance ellipsoid, this x transpose associated with this matrix. So you find the principal axis of that ellipsoid, and these are actually your these U's here are your spatial patterns. So each column in this matrix is an empirical orthogonal function. It is basically a direction in the space of data where there is highest variance. So each U is the pattern that each of these U's are this set of orthogonal patterns that are ranked in order of decreasing variance. And what is this matrix here, V, are the so-called principal components. Effectively, these are the projections of your data onto those directions. Basically, there are time series. Each column vector here can be thought as a time series, which corresponds to the take your data and project it onto the axes that are given by the U's. So this has a nice geometrical interpretation, and it has been a very successful technique in many applications. Now, a potential drawback with this approach of doing linear projections to the data is that basically there is no notion of regularity built into linear projections. And regularity, by regularity here I mean that a linear projection does not necessarily respect the intrinsic geometry of the underlying data set. So this is an example just to show you one of the artifacts that can arise. So you can imagine that we have a data set here which is a very simple geometrical object. It's just a line. But this line is embedded in three-dimensional space, so in this box, in this kind of like a spiral shape, but it's a spiral shape that has this kind of wavy, wiggles. And so we can imagine that we have a particle moving on that line, and this is our data set. And then we do EOF. So if this axis here is basically chosen sufficiently long, this will be the axis that the system has most of its variance. So the first empirical orthogonal function will basically be just the projection along the z-axis here. So to read off the first principal component, we take this spiral and we project it on the z-axis. Now, if we plot now here on this panel the results of that projection as a function of the arc length on this shape, then you can see that it basically has all this sequence of high frequency oscillations, which are not necessarily related to the shape of the underlying object here. This is just a line, but because the line happened to be embedded in space in a very complicated way with folds and so on, a linear projection can introduce all these artificial, not artificial, but let's say not intrinsic to the geometry, high frequencies. So, and this basically, you can imagine that if we want now to study a process that is happening on this line, if if these principal components have this extra oscillatory behavior due to those wiggles, it will be very hard to distinguish, or we will have a lot of the information will be blurred and mixed with this oscillation. So we want to basically to do something about this, basically try to cure some of the deficiencies of linear projections of this type. And one useful way of thinking about possible ways of curing those deficiencies is to basically think of these principal components as scalar functions onto the data manifold. So by that we mean that for each principal component we can go back to our data manifold. So this line in this case, and we can put a number on each point of this, which is equal to the value of the principal component. So in other words, this defines the principal component here defines a scalar function on this object. If our manifold happened to be a sphere, the principal component would be thought of as a function on the sphere. And so if we kind of like abstract away and think of the problem in this way, what we want to do effectively is to make sure that whatever principal components we obtain are actually regular functions of the sphere, on the manifold. They do not have these crazy oscillations, but instead they are they live in spaces of smooth and well-behaved functions, which are intrinsically defined on this manifold. So we will basically try to modify some aspects of principal components analysis to bring in that notion of geometrical regularity. And it turns out that there are natural sets of functions that will do this, and moreover, these functions are accessible empirically from algorithms which were developed by computer scientists for data mining and machine learning a while back. So, to say a couple of words about what these functions are, I will just give again this simple example of the data set was a line, just a line, but a line that happened to be embedded in space in a very complicated way. So if we have a line, which an interval, we know that a set of orthonormal basis functions on the interval, on the line interval, that allow us to do signal analysis and so on, are the standard Fourier sine and cosine functions. So these are examples of these basis functions plotted as a function of the arc length here. So you can see that this set of functions, they do not have the oscillatory behavior that resulted of the embedding, but rather they progressively, as it go up in the spatial frequency of these functions, they describe smaller and smaller features on the line. So we're used to doing that all the time when we do Fourier transforms effectively. Now it turns out, so what is special about the Fourier the functions is that they are also, it's not special, but I guess it's one property of the Fourier functions is that they are eigenfunctions of the Laplace operator on the line. So the Laplace operator on the line is just d squared by dx squared. It's just taking the second derivative, and if you solve the eigenvalue problem associated with that, the solutions are the Fourier polynomial, the Fourier function. So it turns out that analogous objects, analogous, if you wish, Fourier functions can be defined for arbitrary manifolds, and again they arise as eigenfunctions of the Laplacian operators on these manifolds. So for example, if the manifold or the data set happen to be a sphere, then the analogs to these guys here would be the spherical harmonics. And these functions have nice orthogonality properties on the respective manifolds. They form a natural set of orthonormal functions. But for us, what is of key importance is that we can actually compute them empirically from data without actually knowing what the underlying manifold is. So this is done in these algorithms here that basically these are graph theoretical algorithms that they build some adjacency graph from basically the cloud of points that we have observed, and they define discrete analogs of Laplace operators on the graph, and through solving an appropriate eigenvalue problem, that gives you a set of basis functions that have this orthogonality properties on your discretely sampled data manifold. So these algorithms basically are building for us a dictionary of basis functions which have the property that they are orthogonal on this nonlinear manifold that we cannot actually see, but we can find its eigenfunctions. And they have, at least in the continuous case, these functions have nice, regularity properties, so they have bounded gradients and so on. So, and they are defined intrinsically for the geometry. So they don't, if we did a complicated embedding of our data set in space, so long as we preserve neighborhood distances, we would get, arrive at the same result. So I will, because I think I'm going a little bit slowly here, I will just summarize the next step. So once we have this set of basis functions, then basically we proceed by analogy of what is done in singular spectrum analysis. So singular spectrum analysis, if I go back very quickly, if we think of our data set here as as a matrix, and we do singular value decomposition of a matrix. So basically the data set here, we can think of it as a linear map that is taking, if we multiply here with a column vector with some temporal pattern, it will produce a spatial pattern for us. So it's a linear map taking the set of temporal patterns to the set of spatial patterns. And so what we do in NLSA is we generalize that notion of a linear map, but we allow it to act, on functions on this nonlinear data manifold. So we basically define, even though the data set itself is a nonlinear, geometrically nonlinear set, we can still define linear maps acting on scalar functions on that set. And through the singular value decomposition of those maps, we can effectively produce a set of analogous to principal components. So these are the temporal patterns, and sets of orthogonal spatial patterns, and by doing singular value decomposition of this map. And the temporal patterns that come out of this analysis are basically restricted to be describable in terms of those basis functions that we've used, which are the eigenfunctions of the Laplacian. So, once those patterns are computed, then effectively we have a spatiotemporal decomposition of our data set, but that decomposition was in this high-dimensional lagged embedding space. In order, if we want, for example, to create, to visualize how these patterns look in physical space, we have to project them down, and then basically that gives the decomposition of the signal in these patterns. And the hope is that by reformulating singular spectrum analysis through this, there is Laplacian eigenfunctions that, and also because we have introduced some information from the dynamics in the geometry in the first step in the time lagged embedding, the hope is that each of these patterns here will have carry more meaningful information to the actual dynamics than by just doing linear projection. So I will show now examples where how this methodology works in practice. I realize that I skipped a lot of the details. The basic two messages is that we, first, we want to put the information from the dynamics in the geometry. We do this by time lagged embedding, and then we want to produce temporal and spatial temporal modes, which actually are also regular functions on that geometrical shape, and we do that by building this dictionary of Laplacian eigenfunctions. Once we have those, then we can do singular value decomposition of an appropriate linear map, which is analogous to what singular spectrum analysis does. And those will be our, the singular value decomposition of the linear map will give us our spatial and temporal modes. So, okay, so in the first example here, we took output from three long control runs from GCMs. So these were from the NCAR model, your CCSM3, and also the Max Planck model. These were used as a control runs that span several hundred years. So we don't have global warming here. We have stationary or time periodic statistics throughout, and we want to study modes of variability of sea surface temperature in the North Pacific. So this is just a snapshot from one of these model outputs, and the data sets here they are almost to 1,000 here almost, and they are at a roughly 1.5 degree resolution. This basically, once you restrict yourself to the North Pacific sector of the models, you end up with a number of grid points which is of order, it goes up to 6,000. So this is each snapshot of the data set is about 6,000 grid points. But here, as I mentioned earlier, we want to do this time lagged embedding. So we consider histories of the model over 2 years in this case. That brings up the ambient space dimension to very large values, like 10 to the 5. So this is just to demonstrate basically that these algorithms are able to deal with very high dimensional data. The reason that we choose 2-year lagged embedding window is because the seasonal cycle in this data set is one of the strongest external factors, so we want to be able to capture that inside a lagged embedding window. Okay, so, and I should say that it's very important here that we do not do seasonal detrending. So we keep, the data is retained in its raw format. We do not remove the monthly climatology. In fact, the most interesting modes that we find in the system are actually killed if one removes the monthly climatology or does the seasonal detrending. We believe that this is because doing, pre-processing the data by removing monthly climatology from the point of view of this algorithm destroys a lot of the nearest neighborhood relationships that that are part of the raw data and adversely affects the results of the analysis. So, in summary, once we run this pipeline, we get three main families of modes, which some of which are familiar and expected, some of which are, at least to our knowledge, not expected and new. So, in the first class of modes, I guess would be expected in this data set where there is a very strong annual variability are periodic in nature. So these are the annual cycle, and then its higher harmonics going from annual, semi-annual, 4-month, and so on, down to basically the sampling interval, which in our case it was every month. So these are shown. So in these diagrams here, what is plotted here in the y-axis is the singular value corresponding to each of the modes, and the various modes in various families are color-coded in different ways. So you see these periodic modes, they come into twofold degenerate pairs. This is kind of expected because we have sine and these are modes that evolve in quadrature, so they are kind of like sine and cosine relationships. And so then there is another family of modes, which are the modes that are familiar from EOF analysis, like these are the low frequency mode of variability in the North Pacific. So these would come out even if these are the standard modes that come out if one does EOFs in this data set, and they capture most of the variance of the signal. So these are the Pacific decadal oscillation. This is the leading low frequency mode. The second one, which is the North Pacific gyre oscillation, and there are others too. And in addition to those modes, the method here recovers another family of modes which basically are not captured by doing singular spectrum analysis, and because effectively they carry little variance of the total signal, and these are modes which are intermittent in nature, and they are, to show you what intermittent means here, these are examples of the time series of the various modes. You can see, these are an example of the annual periodic mode. These are very regular sine or cosine wave, and these are of the low frequency. The PDO and NPGO are low frequency modes. They have most of the power here in interannual time scales. The intermittent modes have this kind of like modulated structure where they are modulated by the seasonal cycle, but they also have low frequency envelopes of variability, as you can see here, and they can have annual or semi-annual frequencies. The frequency distribution has this kind of like skewed distribution here. So because of the nature of these modulations, the variance explained by these modes is actually pretty small. It's about an order of magnitude less than these modes here. But as I will say in the third part of the talk, these modes are actually can be very important from the point of view of increasing the skill of regression models for predicting these modes. So we believe that they have some dynamical significance because knowing these low variance modes can actually provide a lot of information to have better skill in predicting the low frequency modes. So, okay. So I will show now how these modes look in space. I will play a movie, but this is just a snapshot of the movie. Basically, in various panels, there will be here first the raw data of the model, and then its decomposition into the various types of modes. So there will be the annual, semi-annual modes, this PDO, North Pacific gyre oscillation, and in the bottom row there will be those intermittent modes. So you will see them being activated during certain times and quiescent over other times. The most prominent feature of this mode is here in the Kuroshio current region. There is a lot of intermittent variability there, and also in the boundaries of the basin as well. So let me go to the movie. So this is the raw signal that we put in the model. As expected, has a very strong annual component. This is reflected here in the annual mode. This is the semi-annual mode, is beating twice as fast as the annual one. And here are these low frequency modes that will basically come out of EOF analysis as well. So the PDO has this characteristic kind of like horseshoe structure that arises here east of Japan. The NPGO is active up here in the region of the subpolar gyre and also on the coast of the west coast of North America. And so in the bottom row, you will see that when these modes are active, they describe basically anomalies that are being shed off east of Japan. So you can see, for example, here now, but also in the currents which are adjacent to the Alaska current, or here in the Kamchatka Peninsula. And they come in different flavors, so there are different families of these modes. Some of them have, they all have this modulated character, where they are modulated by the seasonal cycle, or the semi-annual, and so on. So, and these are the types of modes that you would not be able to capture with EOFs. So I will try to convince you, or at least provide some evidence that this can actually have important for the dynamics. But before I do that, I will just make a
Let's ask a question. That top right one, we have the semi-annual
Yes.
fluctuation. Is that due to actual physical forcing, or is that a result of the analysis, which is like the harmonic that's not really part of physical forcing?
It's a good question. I mean,
if you,
it's a time series. So basically, okay, first of all, I should say that the annual cycle is not the monthly climatology. So it is what we call here annual mode. It's not take every month and do the the conditional mean. So the conditional mean of the monthly climatology would be the sum of the annual, semi-annual, 4-month. This is basically decomposing your time mean into this set of harmonics. Now, the fact that these modes arise here is saying that basically this time series or this data set has some variability that is occurring at semi-annual time scale, and this has been observed also in the Pacific. It's not
an artifact of the analysis. It's not just an artifact of the analysis.
I do not believe so. I mean, I think there is.
It's real.
This time series, is a multi-scale time series, and it obviously has a very strong annual component, but it has also other types of. I'm trying to remember. I was reading a paper where they talk about semi-annual variability associated with the I think the currents here in the west coast of North America, but now it's escaping my mind the precise reference. But I don't think this is a.
What I'm thinking of, I'm an oceanographer, so when you analyze tides, you get the basic period, 12.5 hours, but you get overtides, which are sort of generated by, not by the physical forcing of the sun and the moon, but by the shape of the basin and the nonlinearities in the tidal dynamics.
Yeah, so I guess here something similar could be at play in the sense that you have the forcing is at the period of 1 year, but this is a strongly nonlinear system. It can have variability in many time scales which are multiples of that, or like a continuous spectrum of time scale.
Did you just show the part spectrum for this semi-annual mode?
So I didn't show that actually, but it's very similar. Well, okay, this is for the annual mode. So this is for the annual mode. So you can see that it basically has this peak here that's going off the page on basically 1 year. So the semi-annual mode looks very similar, but it's the peak is of course at twice per year, and it looks very similar to that, but with a higher, double the frequency. But I haven't shown it. Okay, so I will make a very quick digression to show some related work that was done using the same method, but for a data set from actual satellite observations in the tropics for Mother-Julian oscillation. So I realize there are many more experts in the audience here than me on this, but this is the data set here is basically this Klaus archive of infrared brightness temperature of clouds. So it is almost I think 24 to 25 year record dating back from the 80s, where it's from different satellites where the observations were integrated in a single data set, which is available, is publicly available, and the temperature here. This is the temperature that the black body, equivalent black body temperature, as measured by satellites orbiting the Earth, are good indicators for good proxy variables for deep convection. So when in the tropics we have these convection plays a very important role, where a lot of dynamical processes are organized around deep clouds and associated waves. So with this satellite observations, we have a high resolution, 0.5 degree resolution observation that is sufficient to capture some of the multi-scale phenomena that are taking place in the tropics, and the most famous of them, I guess, is the Madden-Julian oscillation. This is a very large envelope of organized convective activity that is propagating eastward along the equator, and it has a intra-seasonal time scale, so of order 2 months, let's say, and it is responsible for a lot of the activity in the tropics and on those time scales, but it also influences very strongly the predictability of weather in the extratropics through various interactions. So this is just one example of the structures that are embedded in this signal. Here, if I can show you one, this is from these are observations from the 1992 to 1992, where there was an observational campaign that measured this. So the MJO is basically this. An example here is this collection of clouds that is off the Indonesian continent. This was around Christmas of 1992. And basically this is a very big structure that propagates eastward. It forms over the Indian Ocean and propagates eastwards and influences very strongly the tropics. So basically we want to try to extract that from the data into using this method. So what we did here is we took this data set and we did a projection into a one-dimensional basically equatorial belt. This is average, and as a result, basically we have a time series where this can be the time axis here, and this is the longitude, and you can see various features. I mean, the MJOs are this type of eastward propagating large-scale anomalies in temperature, but you have also other things embedded in the signal. You can see, for example, these two bands here. These are the diurnal cycle in the Amazon region and in Africa, Congo region here. So these are aspects of variability in the data that are much faster than the MJO. They occur in a periodicity of once per day, for example. And so this is a good test bed to see what this algorithm can do, and hopefully also learn something about the data too. So it's work in progress, but I will show you the various modes that come out of this analysis here. So these are the different classes. Again, there is a modes that are related to the seasonal cycle. So again, here we don't do any filtering of the data. We don't remove climatology. We don't do bandpass filtering as is commonly done for signals like the MJO, or we don't remove the diurnal cycle. This is everything is here as presented to us, and the algorithm is able to build this dictionary of modes where they have at least some of them have some physical interpretation, like the ENSO, MJO. These are again twofold degenerate because this is a traveling wave, and also the diurnal cycle. And we can see them in the spatial domain of this data set. So these are the MJO signal, the diurnal signal, and the other types of waves that are embedded in the data. So, and this is how basically the data during this observational campaign was reconstructed, and the MJO patterns are in good agreement with what was actually observed, observation I expect at the time. So, okay, I'm going to go back now to the ocean application and just finish off with at least some evidence that the intermittent patterns, the modulated patterns that we found on the North Pacific have some dynamical significance. And what we mean by dynamical significance here is this will be addressed in the context of regression modeling with external factors. So the problem that we ask is, given the time series of the modes that we have recovered, we want to build statistical, simplified models to make predictions. So namely, given that we have the values of the time series at time t, we want to predict what the values of the time series will be at time t plus delta t through some model that we put forward and estimate its coefficients with, let's say, ordinary least squares or some other technique. And the idea is that we integrate this model forward in time many times. So this delta t time step here is in 1 month in this case, and we can assess the skill of the model in making forecasts. And we can put various things in here in the right-hand side. It's a far non-trivial problem, what kind of structure one should put, especially because, if these terms here are nonlinear in the v's, if the functions here are nonlinear in the v's, you can have a lot of, nasty things happening, like finite time blow-ups, instabilities, and so on. So what we want, our goal here is basically to identify, take a subset of modes that we want to predict, like say the low frequency variables in the system, like the PDO or NPGO, and say what other modes do we need in order to do a good job to predict them. And actually, it turns out that I will march a little bit fast here, but the intermittent modes actually play an important role in this process. So the standard, basically, the standard way of one, this regression setup is presented in the North Pacific is basically that the models that are generally used are linear autoregressive models where there is an external factor, meaning that a mode that is taken as prescribed, which represents the forcing of the North Pacific from the tropical ocean. So this is the El Nino forcing. So and this type of models have some skill that ranges up to like 2 years or so in predicting the state of the ocean, of the low frequency components of the ocean, provided that this mode is prescribed, the ENSO mode. Now, in this framework here, sorry, I'm skipping some stuff here, we put forward a different sort of model where we retain the standard autoregressive term, but we treat those intermittent modes here with the product with the seasonal cycle as external factors. So the reason, the motivation of using these products between the intermittent, the modulated modes, and the seasonal cycle is basically that, if you take, if you think of these modulated modes as having some kind of carrier frequency, if you multiply that with a periodic mode, there will be some low frequency component. So there is so the periodic modes here, so the seasonal cycle is acting as a demodulating operation of the intermittent modes. And the hope is that the product of these two has actually some meaningful information for prediction of the low frequency modes. And we can do the same thing, vice versa, for the intermittent modes. And once, this procedure basically leads to models of much higher skill than what the standard autoregressive model with tensor forcing could do. So here, for example, you can see this is an example where the true trajectory and the hindcast trajectory with those intermittent modes prescribed are in very good agreement with one another, and basically they maintain a very good correlation even to multi-year time scales. Of course, there is a caveat here, that the intermittent modes are treated as prescribed. One can say, how are you going to ever know what these modes are going to be? So this is why we call this pointing to some limit of predictability. It's saying that had we had knowledge of those low variance intermittent structures, we would be able to infer with very high skill what the low frequency dynamics of the system are doing. But then, of course, it's not that we can predict those with any skill necessarily. So, okay, so I think I'm just running out of time, so I will summarize here. I try to provide an outline of this method, which we call nonlinear Laplacian spectral analysis, that tries to bring in some of the geometry of the data set into play to basically produce a dictionary of modes that capture states which are not necessarily thought that have the most variance, but hopefully have some dynamical significance. And I showed you that it allows us, at least in the case of the climate model output, to extract some modes which were not previously accessible through EOFs, and that these modes have some, we believe that they have some dynamical significance. And I said a few words about ongoing work in applying this framework in satellite observations for tropical dynamics. Thank you.
Thank you, Matt. Any questions for Dr. Giannakis? Yes, please.
What is the embedding window in this method?
Embedding window? Okay. So it's so basically this is when you take your input data, so this is just a cartoon up here, but like you can imagine that you have your output of the GCM in the non-Pacific, and instead of calling each individual snapshot as your data vector, you choose a window, delta t, that's the embedding window, and you collect all the snapshots, if you think of them as some kind of stack that lie within that embedding window. And from that you create extended kind of a column vector, and you call that each of these trajectories as an individual data set. And this was done in UF analysis as well. It's definitely a very well established. It's been around from back in the 80s. So this is not, we're not doing something new.
Okay. Second one, please. After you get the modes for the temporal modes, are all those modes independent or assignable to each other?
They are orthogonal. Yes, that's a good question. They are orthogonal, but they have a inner product which is not a uniform weight inner product. So they are orthogonal, but the orthogonality relation comes from the basis functions that we use to describe those modes. So the Laplacian eigenfunctions have an inner product. They're orthogonal with respect to an inner product which is defined on this data manifold. So, and because our temporal modes are expanded into this basis, so they are orthogonal with respect to that inner product.
You said this method provides some mode that can have more physical meaning, but how do you use that?
How, sorry?
I mean, you said this method provides modes can have more physical meaning.
So, I mean, of course it's not a priori guaranteed, but in the examples that we've studied so far, so for example in the GCM case, so these modes here, which were the intermittent ones, we found that are actually, they can be used in regression models and can increase the predictive or hindcast skill of these models by a large amount. So meaning that had you known these modes and you wrote down this reduced dynamical model, you would be able to do a much better job than without them. So that's, for example, one case where we believe that these modes are of some significance. Now, also in the first example that I gave, I didn't show the analysis for this data set here. This was a different case, which was a low-order model of the atmosphere where we did a Galerkin type projection, and basically on doing that projection on the modes of in the EOF basis gave very poor dynamical skill, as opposed to doing the projection onto the modes of obtained by the NLSA method. So obviously, there's by no means guaranteed that it will work. It will do work in every case, or it will give something in every case. But at least so far, we have had some encouraging results.
Yes.
How do you decompose? So you said you can use this for hindcast, and do you have the ability to use the same modes for future forecasts as well?
So hindcast here. There are two reasons why these are hindcast and not future genuine forecasts. I mean, the one reason is that we treat. Sorry if I go back here. That we treat parts of this, these modes, we treat them as prescribed, as external factors. So meaning that somehow you would have to know what these values are in the future. And so we're not addressing the problem of how to self-consistently predict every component of the system. We're saying that which component of the system influence the predictability or the predictive skill of other parts of the system. And in this case, it turns out that the intermittent modes influence a lot the predictability of the low frequency mode through this type of interactions. Now, so in order to do this in an honest kind of like forecast way, I mean, not that this is dishonest, but let's say operational forecast way, you would have to come up with a scheme of, first of all, assigning these values, the future values for these modes. So that could be from another model or and also the other ingredient, which I didn't talk about here, is how do you assign initial conditions, meaning that all these models here are built using the a training data set that we had available in order to build the modes. Now, when we have let's say we observe a new state of the ocean and we want to project it or to assign to it the coordinates that live in where these models operate, then there is an additional step that need to be taken. There are methods that do this. They're called out-of-sample extension methods in machine learning. So we're working on that aspect now.
Yeah, I'm just a little bit confused about where's the nonlinearity in the analysis coming? Because basically what you described seems it's not very clear where it's.
So it is. I have to say I also don't. I mean, I'm not very. It's not my favorite name, but okay, nonlinear. It's because we're trying to basically marry both worlds in some sense. We have this underlying nonlinear manifold that the data set lives that we don't have access to necessarily, but we know that it must be somewhere over there, and it's not possible to do linear operations on a nonlinear manifold. On the other hand, it is possible to define linear structures on a nonlinear manifold, such as scalar functions on a manifold. Because, for example, a set of functions is a linear space, but you can define sets of functions on nonlinear manifolds. Like, for example, on the sphere, we can define spherical harmonics, or we can define functions of the sphere, and these are functions on a nonlinear manifold. So basically, what the nonlinear aspect of the technique is that we define a linear map that acts on, And we basically obtain our mode through singular value decomposition of linear maps. So this is a purely linear algebra aspect. But we construct those linear maps with taking into account the fact that we have these underlying nonlinear manifolds. So they are tailored, through these basis functions. They are kind of like custom made for the underlying nonlinear manifold. But I agree that it is a little bit.
So another way of saying that is the system is nonlinear, and the basis functions are derived from that. They are not imposed from the outside there.
Yes.
So, but then the algebra becomes
the algebra, yeah, because then we, so the basis functions are computed empirically from the data.
From the data which has a nonlinearity embedded in it. Which is nonlinear as we know it, because the equations that describe it are non. So very good. And so thank you very much, and let us thank Dr. Giannakis for such a very interesting seminar.